It is my pleasure to introduce our next speaker, Dr. Mariam Kiran, the group leader at Oak Ridge National Lab Quantum Networking and Communication Group. Her research focuses on engineering self-driving networks, and you also see that in the title of today's talk, exploring AI and ML solutions for improving network performance, flexibility, high-speed distributed data transfers for science. And she knows about how to apply this to wide area networks, wireless and 5G, and beyond, all the way to quantum. Mariam, we are very excited for your talk. Please take it away.
Thank you, Marlou, for the invitation, and thank you to Womanium for inviting us. So as Marlou mentioned, I'm the group leader for quantum communications and networking at Oak Ridge National Lab. My own research is to do AI for computer networks. And I started off with classical networks, and now I've started to move into quantum networks. So my talk kind of covers the basics of AI and how we've been innovating computer networking using it. So to start off about me, so my background, I did a PhD in software engineering from the University of Sheffield in the UK. So I, at that time, did AI PhD, applied to economics and HPC facilities. So it kind of like fit very nicely in the domain of all of those three different fields. And then that led to us developing this open source software, Flame, which was the only software at that moment which did agent-based modeling at that time, and it could allow you to build biology and economic models, etc. It became very successful, worldly recognized, because we had a team of us PhD students who were behind it, and that was one of the successes after coming out of the PhD. It also taught me a lot about how to do open source software and why it's so beneficial for your career. So think about these things when you're working on your software. So at that time, there were only postdocs available in cloud computing. So I did a cloud computing postdoc, and that led me to an internship at Lawrence Berkeley National Lab in California, where I was trying to understand how software can optimize networks. So that was just a 3-month internship, but that was actually a very good internship because they really liked my work and they had a few positions open the next year. So I applied again as a research scientist, and then I ended up in California working on computer networks. So my career kind of like moved from software to computer networks at that time. And when I was given a chance to start my own research, I tried to merge my fields together. So how can the software and AI work I was doing be used to control networks? And as a result, my research now kind of coins this term self-driving networks, and I try to merge those two and come up with those. Recently, last year, I was offered a group leader position at Oak Ridge because after working with wide area networks and wireless networks, I was interested in seeing how AI could be applied in quantum networks. And Oak Ridge actually allowed me to do that. So that's why I moved from Berkeley to Oak Ridge in Tennessee. So it's been a career which kind of moves across geographies, but I've enjoyed my research as I've gone over the years. So the agenda for today is I'll start with a precursor of AI, like what is AI? So this is especially targeted to the students who are attending so that you can understand some of the nuances which people talk about when designing AI solutions. Why is it so relevant now and why is it such a hot topic? And how are we using it in networking to optimize our networks? So I'll try to zoom through most of it because I want to leave some time for questions at the end. So the basics of AI versus machine learning versus deep learning. So these are the three terms you hear everywhere, AI/ML/DL. What is the difference among the three, and is there any difference among the three? So let's start with science fiction. So a lot of us who are the older folks here growing up in the 1990s and the early 2000s, science fiction was very much into our books, into movies, into comics, and this goes back to the 1950s. So these are some pictures of some very famous movies here. Matrix, Futurama, there's Doctor Who for the UK folks who are attending. And it's brought a lot of these main ideas of how AI and human interactions can play out in the real world. So this is where basically I draw a lot of my own ideas from. So science fiction. So if I'm low on ideas, I'll watch a movie or something. So going back to my childhood, so at that time, Windows PCs were the big thing, and you had computer games on Windows that could allow you to play games with the computer. So AI can go as far back as forever, right? So you were playing chess with your computer in the late 90s, and a number of innovations were also coming out at that time as well: speech recognition, image recognition, robotics, the philosophy of mind, like how can an AI think like a human does? So that's been a hot topic since the beginning of computer science, actually. So what is the difference between these three? So I found this picture in an NVIDIA blog, which kind of explains this very, very nicely. So starting from the 1950s, so this goes back to the first ever paper written on AI by Alan Turing, who wrote the paper, Can Machines Think? So in this particular paper, he argued about this Turing test, that if you're talking to a machine and if you cannot make out that if it's a machine or a human at the other end, you've achieved and passed the Turing test. So that's the ultimate test of becoming a very intelligent AI system. And some of the recent movies also showed this. So Ex Machina, this is a still from there where they bring this person in to talk to this robot and try to determine if they've passed the Turing test or not. And this is what everybody's working towards, that they have to pass the Turing test. So that came out in 1950s. And it's been there. They've been developing certain things to do spam filters. HR is using it to go through CVs very quickly. In the 1980s, they started research called machine learning, where a lot of algorithms were being developed. So deep learning actually came out in the 1980s. It only took off in the 2010s because of the advances in GPUs and HPC processing, because before that, there was a massive amount of data. It was very slow to process. And it was not possible to do in very quick time. In 2010s, people actually started using GPUs and HPCs to process this very, very quickly. And that led to this explosion of how we see AI today. So mainly it is being used for image and speech recognition, and it's led by commercial applications, but there is more and more academic research happening behind the scenes. So AI itself is an umbrella term. It encompasses a lot of things. So optimization, expert systems, neural networks all come under this. And within that, if you go into neural networks itself, deep learning, convolutional neural networks, and everything comes under that. And the main difference of neural networks compared to other AI techniques is that you learn from data given to you. So optimization is you'll write an algorithm to optimize certain things or resources. But if you have data and you're trying to learn what the function that can best map this data is, that is, those algorithms would be turned under machine learning. So that's how you can differentiate between these things, but all of them are basically AI techniques. So even if you're doing optimization and swarm intelligence, evolutionary techniques, those are also AI techniques. So there's a lot of deep learning libraries that exist. Scikit-learn is a great way to start. It's a Python library, which you can start with, and a lot of people still use it in their code. HPC is becoming very, very relevant to do data analysis and simulations and analyze these massive data amounts. You can also do quick training on HPC, such as model and data parallelism, where you can divide the data into chunks and over multiple processors so that you can get quicker results very, very sooner than waiting for days for your computer program to finish processing those. And a lot of new research, such as at conferences such as NeurIPS and other deep learning conferences are constantly publishing papers in these new invariants and innovations, and people trying different techniques in how they can optimize a neural network or learn better things. So DeepMind was initially, they started deep Q learning for Atari and the game Go. And then recently, OpenAI, also held by Microsoft, is now innovating large language models, GPT, ChatGPT, et cetera, is coming out of OpenAI. So some of the very famous libraries in deep learning are these four: Caffe, TensorFlow, Theano, and PyTorch. TensorFlow and PyTorch are the most commonly used now, and that's where you will see a lot of your work will come from. TensorFlow is from Google, and PyTorch is from Facebook. And people have preferences in both of those libraries, so it all depends on you as a programmer, like which library you're more comfortable using it. So let's go into machine learning tasks itself. So we spoke about the libraries and what AI was and how it started. Now, machine learning itself could be grouped into 3 different categories. So you can do regression, where you are predicting some value in the future. So you can do linear graphs, for example, to extend that line and see where a predicted value in the future would be. Or you could do classification. So for example, if you have a group of data sets and you want to group them into categories, that everything is red falls under this category and everything is black falls under that category. So you could do that kind of a classification and group it based on data sets. And then there is clustering, where you again do the same thing, but this is unsupervised. So you don't know, you don't have labels on the data sets, but you kind of like whatever is closer to something, you kind of try to move things into clusters. So in all of these 3 techniques, you have different algorithms that support each of those 3 techniques. So once you identify what task you want to do, you can then see what kind of algorithms you want to apply to it and then use that in your work. So how would a machine learning thing work in action? And most of you might know this, but just to drill this idea in further. So you start with data, which is available to you, and this is the training phase. So here you've collected a lot of data and you want to apply machine learning to a particular data or a problem set. You then write a machine learning problem that can model this data and either learn f of x or learn clusters or classification on that particular data set. You train that machine learning model and then you write it out. So once that machine learning model is written out, it is now ready to be applied on your data. So then you have this test data concept that this is data which the machine learning model has not seen in the past. You run that through your saved machine learning model, and then you can predict what the label of that particular input is. So this is how machine learning kind of works behind the scenes in action, with mainly these 3 steps. And I'll go into like what is the difference between the training data and the test data in the next few slides. So eventually, you also want to make sure how accurate your machine learning model is as well. So this comes under you measuring how well your machine learning is predicting the correct number of predictions. So for example, you can have different machine learning models giving different accuracies on the same data set as well. So here I have a graph where I'm trying to classify flows over a network, and I'm using random forest, extra trees, and gradient boosted regression trees, and each of them is giving me a different accuracy. How do you measure accuracy? Is number of correct predictions divided by the total number of predictions. So this is how you would end up choosing what is the best machine learning model for your particular problem set. So when you have a full data set, you divide it into 3 chunks. So there is training data, which could be 50% of that data, which determines like what you train your machine learning model with. Then you have a validate set, where you can check how good your machine learning model is performing. And then is the test data, where you actually measure the accuracy of your machine learning model. You can also divide it into 2, where you just have train and test, and you don't need to do validate, but some software programmers use validate just to improve their performance of their machine learning models. And then eventually you get this kind of graph where you produce that and say that this is the best machine learning model I'm going to be using. So in this particular case, random forest is giving me the best results. So when I do actually deploy my machine learning model, I will be deploying a random forest algorithm in my technique. So now that we did a very basic on what machine learning is and what are the basic terms that people should be aware of, why is now such an exciting time for us AI researchers to basically be living, right? So So a lot of these concepts, when we were doing undergrad, we were only reading about this in books and seeing these in movies, right? But actually, AI has taken huge, big steps in the recent few years. So deep reinforcement learning, learning through brute force, such as AlphaGo and games, was a breakthrough in 2017. So everybody remembers this famous picture of the Chinese player recognizing that he's finally lost to the computer. So that was the AlphaGo training using deep reinforcement learning, where he could beat the person on Go. And that technique has been adapted in self-driving cars and also in vision to recognize cats and dogs. So that was where the major contributions of machine learning has been. And then, so since then, a lot of new work has started where they started to use machine learning in identifying objects in images and how they could do much more better classification over cameras. And then recently, ChatGPT came out with generative AI. So here they developed these GANs and large language models where you could basically talk to a bot and then try to get answers from it. So it's learning from millions of data points. It generates its own fake data if there is missing data, but it's basically learning patterns from the initial data set that was given to it. And it's been used in writings, in paintings, in creating images, and also they're using it in movies where they're superimposing the hero with some other character sometimes if they want to see someone else playing that particular role. So those are huge, huge AI big steps where they've actually realized a lot of the concepts we only read about in books. And now we actually see this happening. And a lot of the libraries now allow you to easily build these models also. So that's also the another innovation that has come, that anybody can start learning how to write an AI model and write their own approaches to this. So if you have time, so sometimes we have time, so I play around with these things. So DALL-E is OpenAI's image generating app. So you could put in text or in this particular app. So I put in cow sitting on a rocket flying to the moon, and it can produce images for the text you've written. So it's very nice if you're doing a presentation, for example, and you want to find an image which you can't find. So I can create that on DALL-E. So as you can see, it comes out with different versions of this. So this is a cow, which the rocket actually looks like a cow going to the moon. Or the second version is the cow actually sitting on the rocket looks better. But you can also add more data to this. So say that you want a pastel version of this particular image, and it produces a pastel version of this image of a cow going to the moon. Or any artistic style. So Van Gogh is an artist which a lot of the AI techniques are trying to copy as well. Now, as of now, you own these images. So OpenAI does not own these images. If you've created these, you own these. So a lot of people have started submitting these images to art competitions or selling these images as art. And there's a huge debate in the art community whether this is a good approach of AI as well. So this is like something fun for everybody to do on the side. It's sometimes not very accurate. So I put in more text like Cheshire Cat hanging in a tree and comes out with these horror images of some eyes are missing, etc. Or cats doing yoga, which are doing some weird things, which I've never seen my cats do. So it's fun to play with this, and it's innovative to see how it's kind of coming up with these techniques also. So I'm always interested to see how it's actually learning this behind the scenes. So that's another interesting direction to go into as researchers. So the other experimentation with ChatGPT, which is happening right now, is people are using this to write chapters and essays and plays. So for example, if you put in the same way as I put in DALL-E that a fox jumps over the moon, it will come out with a scene play of what happens when the fox jumps over the moon, for example. So I've used it, for example, to test it out. I used it to see if I could write a section for one of the papers I was writing on how TCP congestion control algorithms compare against each other. So I said, can you write me a section on related work on these TCP fairness studies? And it actually gave me a section, sure, this is what it looks like. TCP BBR is a new congestion control algorithm, and it goes into the details of those. However, it does miss the references to where it is getting this data from, so I cannot actually use this section in my paper. But it's good if you are going through a writer's block and you're trying to find some ideas on what to put into. And obviously, you have to acknowledge this in your papers if you are using ChatGPT or similar techniques to write sections in your papers. Another technique which we're using this for example, if I have to configure a router and I don't want to sit and go through like lots and lots of manuals to understand how to do it, you could put this into ChatGPT, and then it will give you a step-by-step process on how you can actually connect a router to the internet and what processes you have to go through. I've communicated this back to network engineers, and they say that some information is missing from this because ChatGPT misses out on some of the experiences engineers have had in trying to install these routers. But it's a good way to start, and it saves a lot of our time when we're trying to install something and we don't know where to start. The other approach is where you're actually, for example, installing Grafana in InfluxDB. So this is something which I'm trying to do. And initially what would happen is I would Google this and it would come out with 10 different pages where I'll go through and see what the instructions are and try it out on my machines. So ChatGPT would give all the instructions again in one page, and you could use that to actually install Grafana and do InfluxDB, etc. Now, in my own experience, if I get an error, ChatGPT doesn't know how to solve that error right now. So I still have to go to Google and try to find out how to solve that error. But it is coming closer and closer to getting a good solution, and it actually is saving a lot of our time. So Copilot is also a very big advantage ChatGPT is giving in terms of programming. So for us coming from a software engineering background, we know about agile software engineering, where you sit as pair programmers, where one person programs and the other person kind of watches and improves the code. GitHub now has a Copilot, which uses this to actually provide suggestions, improve suggestions, and actually adapt it in the code. So it is impacting coding time as well, and it's changing how we normally did programming ourselves. So you can see these are some examples of how AI is definitely impacting our day-to-day work as engineers, where we're writing software for our research also. But it's not just hype. This is a trend graph of how ChatGPT trends have been over the last few years. And as you see, it was launched in 2023. And there's been a huge surge of people who are interested in using ChatGPT for any of their work. But it is very biased. So all ChatGPT does is it gives you results based on the data that is already available on the internet. It does not do any inference on its own. So this is where the engineer said that we have a lot of experience of 30 years, which we've tried out things and we've learned things over the years. And ChatGPT, if it's not available on the internet, would not output that as one of the outputs. Just a fact over here is some people actually use it for code checking. Like they write their code and they put it on ChatGPT to check if there's any errors. You should not do this if your company policy does not allow that, because that is proprietary code. If you put anything in ChatGPT, it's gone. It's on the internet, and it's not it's not your propriety anymore. So people have been fired for doing that. So you have to check your company's policies before you start experimenting with any of your company stuff in ChatGPT. And goes for your personal code as well. If you don't want it to be out on the internet, refrain from using ChatGPT. But it's good if you're learning certain things, and on the side you can keep it. So how is AI impacting science and our networks also? So when we think about AI, we think about HPC facilities, but we don't think about the network as much. So I come from Oak Ridge National Lab. Oak Ridge National Lab is one of the DOE's national labs. So as you can see, this is a map of the US, where we have 15 to 50 national labs, all distributed across over here, tackling scientific major challenges from climate change, discovery of galaxies, and we're also building autonomous labs, such as the ones at Oak Ridge over here. DOE, or the Department of Energy, actually maintains these, and they have unique infrastructure in terms of HPC facilities that are available at all of these labs where, for example, we have Frontier in the picture shown below, which is #1 in the world, and it's been #1 in the world for the last 3 years as the top 500 supercomputer in the world. And we're always competing with the other supercomputers across Japan, China, etc., and we've maintained our supremacy over there. So you have all of this massive amount of compute power at your disposal. So imagine the kind of AI work we can do, right? So AI has been at the forefront of our research. So we use AI from climate change to discovering galaxies, and we're also using AI to optimize the network. So all of these facilities that are shown in the map over here need very good networks to connect them, because data can move at high speeds and people don't have to be geographically located at certain places to do research. So that is where networks are being optimized to make sure that scientists can communicate and collaborate over large distances. The other aspect, what we are seeing as scientists, is that the data that is moving across these networks are growing at exponential rates. So the DOE's network is called ESNet, and that's charted like a 50% increase in data rate that is moving across these networks like every year. If we maintain the current infrastructure as it is, we will run out of space very quickly. So we have to keep innovating the infrastructure, the networking infrastructure, so that we can cope with these growing data demands, which the computing people are doing on our networks. The other aspect is networks are going outside our lab borders. So we have more and more scientists who are using IoT and edge devices that are being installed out into the fields, where they're doing research in biology or ecology or water dams, etc. So how do we get that data into our labs so that they can process it? So wireless networking, which wasn't a big thing until recently, has become huge for science domains as well. So we're looking at how networks in wireless can also be optimized using AI, for example. The other aspect, which is also happening right now, is the evolving edge. So now we have very powerful sensors. So people talk about their mobile phone having so much of supercomputing power in their pockets now. So the same way, sensors also have a lot of compute on them. So you could do GPUs or FPGAs being installed at the edge, and you can do a lot of processing at the location, at the sensor itself, before the data is even moved somewhere. So we're looking at these evolving edges. We're also having these quantum devices that are also being developed, which are also going to be on these edges. So how are those going to impact the networking infrastructure that connects everything? So how do we use all of this information to engineer self-driving networks? And I'll talk about why I'm particularly intensifying this engineering aspect in self-driving networks. So in AI, what we're doing in AI is how can we use the infrastructure as it is and make it better? So for example, this is a very nice cartoon of a networking infrastructure shown by 3 routers, and you're collecting all kinds of network telemetry like flow data, how many users are on the network, if there are any bad actors on the network. So you can create a lot of data sets just monitoring the data coming off of the network. And you could do a lot of machine learning on top of that data. So you could do supervised and unsupervised classification, anomaly detection, and you can also do forecasting. So you can identify any bad patterns that are happening on the network before they actually do anything that is disastrous on the network. Once you have identified that, you know sudden anomalies because you've learned previous patterns over the network, and then you can take corrective actions also. So you can automate a lot of the infrastructure to correct itself such that humans don't have to be constantly sitting and monitoring what is happening on the network. So this is very advantageous because all the daily menial tasks, you can offload that to an AI. There are some tasks which the AI could do overnight, so you don't need to call engineers out at 3 a.m. if something's going wrong on the network or if a line goes down. The system itself can recognize it and divert traffic to make sure that it's going smoothly until the engineer does come out in the morning to see what happened. So this is just one example of how we're using AI in networks, but you can see similar examples of how AI can be used to optimize computing infrastructure also, where you can identify certain processors that are going down and how could you redistribute the load across other computing processors. So recent advances in network hardware actually allows us to do this, because previously what happened was everything was closed off. These companies owned their routers and switches, and they did not give you permission to access these hardwares. Now, more and more companies are opening these up. They're giving APIs where you can write software to interact with that hardware. So open source definitely has opened up a lot of techniques for that. Software-defined networking, programmable networks are some of the techniques that are actually allowing us to have AI interact with networking hardware. There are recent test beds that have been produced, like Fabric, P4 Labs, and all of these have been funded by US, NSF, and DOE organizations that also allow researchers to write their own techniques and test them out on how these kind of AI techniques can interact with networking infrastructure. So there is a lot which is happening now that allows you to do more innovative work in this area. So looking at networking AI as an engineering task. So this is something which I try to do as an engineer myself. You always have to start with what the question is. So what is the thing which you're trying to optimize on the network? Because you can apply AI at multiple things, right? But you have to really drill down on what you're trying to learn off of. So I asked the question. So the question could be, I'm seeing a lot of heavy flows on the network that are causing my network to congest. So I want to identify these network flows before the congestion happens. So once you ask the question, you can see what kind of data sets you want to see, which will help you solve that question, observe and analyze, take action, and then test. So in that process, you would come out with massive amounts of diverse data sets. You identify, these are the flows I need to look at. I don't need to look at, say, performance data. I only look at flow data. Then you identify which kind of AI model it is, and which should you use and why. How do you take action that once the AI gives you the result, how do you integrate this back into the device? And how long before you know that whatever you did was good, or is it damaging the network also? So testing becomes a very important part of using AI in networks also. And if you look at this as an engineering task, it actually solves a lot of the doubts people have on how AI can actually help us in our work. And within AI, you can again group it into those three categories I started with. So either you do classification, regression, or prediction, or you can do reinforcement learning or control. And each of these three techniques differ by classification and prediction. You need data to do these kind of algorithms. Or if you're doing control, you can actually write an AI algorithm that will learn by doing things on the network. So you don't actually need to start with data sets to do control techniques. So I'll go into the examples of each of those three and how we've kind of innovated the network based on those. And these are very simple ideas which you can use in your own work as well. So let's start with classification, where you need data to start with. So you'll build a data set first. So you'll set up a network, as you can do on Fabric test beds or just between two server and a client. You set up a network and you send data down it, and then you can collect your flow data coming from it, like what was the performance of the flows moving on the network. So you build a data set by just the initial run. Then in the second phase, you try to introduce anomalies on the network. So for example, you can introduce congestion, and there are tools by which you can manufacture anomalies on the network. So once you are putting in anomalies on the flows, then you collect another data set. So in essence, you can have two data sets, one when everything was good and one when everything was bad or anomalies were introduced. Now, once you have those kind of data sets, now you can start playing with things. So you could either do supervised learning, where you do have labels on these data sets in this particular example, and then you can group them that this was the good flow and this was the bad flow. So that is exactly what I did in this this picture on the right over here, where I collected normal flows where nothing was happening on the network. And then I introduced loss and duplication and those kind of situations on the network. And once I did a principal component analysis, kind of like just grouping the flows in, I saw that all normal flows fell on one side of the graph and all abnormal flows fell on the other side. So this is how you could do classification or group identification by having a label data set. So and in an unsupervised thing, so for example, if I didn't have these labeled data sets, like you just did collection of flows over time, and you don't know when certain anomalies happened, and you don't know if certain flows are happening during anomalous times, you could still create a graph like this. And you can identify that there are two distinct clusters coming out. And what are the characteristics of these two clusters? So and then start digging into the features of each of those clusters. And then you can recognize, oh, this is a cluster that has all good flows, and these are the clusters with the bad flows. So that in the second case, you actually start with no label, so you don't know what is happening at the time and how those data sets are being clustered over here. So unsupervised, it's actually a very powerful technique to identify certain things which you don't know when you start with. So we've done this, for example, on pre-COVID versus post-COVID data sets. We looked at data sets that were before March 16, 2020, before the lockdown happened, and flow data that was after March 16, 2020. And we were looking at whether, so these were unsupervised clustering, and we were trying to see if there was some difference in behavior of the flows that were happening on the network. And we did find that there were more distinct server connections and changes in traffic profiles because people changed their their working patterns during those times. And we saw that in the network flow data that was coming because we saw like two different clusters happening. And then once we drilled in further, we found that most of the people were actually working after midnight in post-COVID times. So that was like the stark difference that came out when we started studying these clusters in detail. So another technique of using clustering and anomaly detection, which we've been doing, is to do radiation detection. So we're using this in 5G networks, where we're adapting the LiDAR, the video, and the environmental data on the sensor itself. And we have an anomaly detection algorithm that sits at the edge. So basically what it is doing is it's reading an information live from the surroundings, and it's seeing if there is any radiation in the system. So for example, in this particular video here, which I'll only run for 2 minutes. So in this particular scene, we have this Raspberry Pi connected to these detectors. And the detector is basically has this clustering anomaly detection algorithm for radiation detection. And it's sitting on the table, everything is fine. It's reading in the gamma counts. The anomaly metric is basically 0 at that time. And what happens is that at this particular time, the student of ours introduces this plate next to the detector. The plate is from the 1950s, where they have this uranium-coated pottery at that particular time. And because it's uranium-coated, it has radiation on it. So as soon as that plate comes closer to the detector, we see that it suddenly starts to recognize this anomaly in the environment, and it's basically flagging that up as there is radiation being detected. So these are techniques which is just doing clustering or classification at the edge, and the data doesn't even need to move over the network at this point. We just do this at the edge. We recognize something is happening, and then we can take corrective action straight away. So this is a powerful technique, just simple clustering algorithms you're using. And yeah. So the second approach is to do prediction or regression. So we've been using this to predict future network traffic. So for example, we have traffic which we're collecting now from 0 to n. What would n+1 and n+m look like in the future? So the way we do it, we read in the network as a graph. All the sensors become vertices, and all the edges or the pathways in the middle become edges. And then we can build adjacency matrices, and then we train a graph neural network based on that. And this is like the simplest graph neural network, which this is all open source code, which we adopted for this particular case, where we did an encoder-decoder model. You train these input sequence of time series data, and you try to predict what the future time series data is going to look like. And you throw data back and forth until you come out with a good neural network that can map that. And once it's done, you bring in new data set, and then you again try to predict what the future data sets are going to look like. So we've done this in this, and we've also compared it to other prediction algorithms like ARIMA methods or recurrent neural networks or LSTMs. And we found that graph neural networks actually give you a better prediction accuracy than any of the other prediction accuracies. And these are, again, ways in which we're testing out different machine learning algorithms and trying to determine which is the best one for the problem we are investigating for our work. So just another thing we also tried was how much of an input data set should we give to get the best predictions in the future. And in this case, we're trying to predict for the next 24 hours. So we played out with, okay, should we give a 6-hour input versus 12 versus 24 versus 48? And we tried a few strategies, and then we found that 30-hour inputs actually give you the best 24 hours of prediction. So you will ask, like, why is this important? So as a network engineer, if I can predict what my next 24 hours are going to look like on the network, I can go in and do corrective actions now. So to prevent any congestion or bad things happening in the future. So people can use this in road traffic, city planning, or any other, even weather prediction, for example, uses these techniques quite a lot to predict where it's going to rain in the future. So, so these are the same techniques being applied in networks. The last case is actually the most interesting one to me, because this one is where we're learning control when there is no data available. So this falls under reinforcement learning, where we learn via trial and error. So an agent sits, monitors the environment, tries out different actions, and gets a reward based on what it tried. Through these interactions, it learns what the best strategy was and what I would do if certain things happened in the future. So this is that thing which we're developing, that we could just offload everything to the AI agent, and then that would manage everything on the network, and human can actually relax and do other things in that sense. So for example, in this case, we're trying to see how the AI could learn better optimization strategies for routes compared to the shortest possible route. So in networks, we still use the shortest possible routing algorithm to calculate the distance to go from a source to a destination. And that could be done in advance, where you program that in, and then you put it in the system, the network, and the network follows that. We don't want to do this in advance. We want an AI to learn the best strategies, and it can optimize the network itself. So humans don't have to do this prior work. So we envision this as a deep reinforcement learning problem again. The same network, we're learning all kinds of network telemetry that is coming off of it. And then we train a deep learning model for it, where the learning model can try out different strategies. Like, if I go this path versus this path, what is my reward? And the reward in this case is either my flow completes quicker or the latency that is observed is low. And through this trial and error method, the deep reinforcement learning software can actually learn the best strategies for path calculations on the network. Now, this itself can be divided into two different categories, model-based versus model-free. Model-based is where you do some sort of model learning before, so you do some prediction of the future, and then you make your decisions based on your predictions. Or model-free is where you just learn from experience. So one very good example of thinking about this is that if I have to go to the airport, if I open up a Google map and I plan my route, that is a model-based approach because I have a model and I'm planning my route based on that. A model-free approach is I've been living in the city for 5 years. I know that if I go at 5 p.m., there's going to be traffic on this particular route. So I'm going to take the other route. So that is based on experience, and that is model-free learning. It takes longer because you have more time to learn all of these different strategies than a model-based approach. But it is definitely more powerful because you can learn certain strategies that a model-based approach would not learn otherwise. So we've been building this into a traffic engineering solution where, again, we have a network. It takes in all of this network data, topology, health, and traffic patterns. It does prediction, like what my paths are going to look like in the future, and then tries to come up with better routing tables that can then be sent down to the network that will eventually lead to a latency-aware, utilization-aware network, which we wouldn't have done if we just followed the shortest possible route technique. And these are some results in simulation where the AI software is trying to try out these different strategies and learn like the best traits, and then it uses this to inform the future network updates. So these are like some results of that. Like before we turn it on, you see that because we're always using the shortest possible route, there are cases where one link is always going to be used. And then in this particular case, link 4 was overused to 34%. And as a result, you get congestion on that link. When we turn the AI on, because it's learned all the different links and patterns, it can actually help you do better load balancing. So in this, after it's turned on, we see that the link 4 is only used to 17%, where other previously unused links are now being used more and more. And we get a better load balance across the network. So now you can actually do more things coming out of your network. You can send more flows. You can have more and more data being added to the network without any resource problems coming into the future. So these are some examples on how we're using AI, but it can also help with breakthroughs in networking research. Networks are becoming more and more intelligent because there is so much more compute power that can be brought into networks. So we can now install FPGAs at edges where you could do classification and in intelligent things on the edge before data even moves on the network. So there is more innovation that us as network engineers are now doing for sciences. We're also looking at eco-efficiency solutions because AI is so expensive energy-wise. We're trying to find what is the best trade-off for accuracy versus energy. And as a result, we're doing a lot of our own research in 5G networks where we're building our own 5G testbed using open source RAN controllers where we have Raspberry Pis with 5G hats or antennas with our own program SIM cards. And then we're building all of this infrastructure, the base station going up to the 5G core that eventually connects to the wide area network. We're using open source for this because we don't want to be tied into one company. We want this horizontal expansion that as we expand over the years, we're going to say, okay, we're going to use this from NVIDIA or we're going to use this from Microsoft. So we want this horizontal expansion, especially for researchers, so that we can try out different strategies. And energy efficiency is key here because recently there was a statistic that AI is using up to 9% of the total world's global energy, and we want to see how we can optimize this and build better energy efficient AI solutions for our networks. In addition, we're also doing quantum networks at Oak Ridge. So this is the idea that quantum data is going to coexist on top of optic infrastructure, and it's called coexistent signals. And my team is going to be doing additional talks in the next few weeks to talk about that. So stay tuned to Womanium. So the whole point is that we have an networking infrastructure that already exists, which we're using for the internet. Now imagine that this has quantum devices superimposed on top of it. Why would you do quantum devices? Because now you can do more science. You could do more precision measurements. You could do more innovative science that are only possible using quantum devices or physics devices at the edges, which are not possible with compute devices. So we are building the network to make this possible because you have different quantum devices and you need to make sure that they are all connected and distribute quantum states through entanglement. My own role over here is looking at how AI can help with some of this work. So recognizing quantum states and optimizing the quality of the photons being produced. So Oak Ridge is a great place to do this work because we have our own quantum network testbed where we've been setting this up for the last 6 years and we're doing more and more research in this. So my team is going to be doing some more talks on how we're actually building the quantum network behind the scenes over here. So the vision which we have is that we're trying to go towards this scaling of the quantum internet. So quantum networks are very good for cybersecurity and quantum key distributions, but we're also looking at how in Tennessee we can extend the network we have on site to neighboring states and more. So there is a lot of research that needs to happen behind the scenes on developing a quantum internet, like repeaters, controllers, etc. So our group is heavily involved in this, and we've done a lot of papers and recent publications that actually help us with this, and we'll be talking about that in the next few weeks. So in conclusions and forward-looking, so from talking to the students here, so think about what inspires you. If you need to take inspiration from movies, or better yet, talk to the users who have problems. So I talk to a lot of the scientists who use our networks, and I identify what problems they are having. And then I build a solution to solve that problem. Because you should always think of, if you're building a solution, why would someone use this? If I build an AI that can optimize, say, load balancing, why would it be important? And then that kind of like helps you develop your solution around that. Think about end-to-end solutions as well. Again, how does this impact your users? Because as software engineers, we are trained that people should be using our software. So think about these ideas when you are building your projects over here. Collaboration is key. So I've done this a lot in my work. I'm a computer scientist. I collaborate with physicists. I learn off of them, they learn off of me. So it's all about collaboration in science, where you can share data, you can share resources and tools. You can think of building your software into repositories, documenting your code, and sharing this again. So the more and more input you get on your work, you can improve it and people will use it more. Yeah, and then finally, that is all. So leaving you guys with a quote. The world is going to be more and more AI driven. IBM had this quote in 2003 where they envisioned that systems will be learning to manage themselves. And then as soon as a new system comes online, it just integrates into the fabric like a human body cell does. That's what I see networks going as well, that all the labs are basically managing themselves, and then new devices come in and they basically self-integrate into this wider fabric. And that is what we're trying to strive towards and use AI to help with that. And that is, that is all from my side, and leaving room for questions.
Fantastic. Thank you very much, Mariam, for this really exciting talk.